Hello students, in the last video we have discussed about regular grammars and unrestricted grammars. So in this video, the last video of ALC, we are going to discuss about context sensitive languages and linear bounded automata. So according to the hierarchy, the machine to recognize the context sensitive languages is linear bounded automata. What does it mean, right? The linear bounded automata, right? So which is bounded means the size of the tape is not infinite here. So it's like Turing machine is not infinite. So the size would be decided based on the input tape. So to find the length, we have to take the length and a constant. So then this function will find the length of the input tape before constructing the linear bounded automata. Right. So memory information, how much memory we are going to use is nothing but a particular constant into input information. So constant means we cannot change it. That's the meaning. Once the process has been started in Turing machine, we can use the infinite type, right? But here it is going to be bounded. You cannot go behind it, even though maybe the tape may be having infinite, but you are not go behind that, right? So how it is going to be here? We are going to specify with the left hand and right hand markers. As I told you, even though you have, then you cannot go behind the space. You are bounded with the markers. And how much size this is going to be identified, as I told you, so we need to identify some constant and also the length of the input tape. So that will decide what is the length before starting the process. This is the only working space. We cannot use that thing. It moves in both the directions, same like Turing machine, right? It moves in left to right and right to left, and it changes the input symbols and read it. Everything is same like Turing machine. But the only restriction we are having here, can't go behind the left hand marker and behind the right hand marker. Then the linear bounded tuple notation is denoted with the 8 tuples. So like Q is a set of finite states as usual. X is the tape alphabet and sigma is the input alphabet. So tape and input alphabet different, right? Q naught is the starting state. ML is a left hand marker and MR is the right hand marker. See transition function, same thing. Whatever the transition function we have used for the Turing machine, and F is a set of final states. So what are the languages accepted by the CSL? There are some languages we have given here, right? Okay. So N is a perfect number. Okay. Some languages, I just mentioned some. We'll construct the LBA for this language in this video. We'll do over that. Then let me go with this example, how to construct it. A power n, b power n, c power n. See guys, first let me tell you how to construct the Turing machine, then we'll convert into the LBA, right? So the Turing machine, A power n, b power n, do you remember that? So if not, just let me go with this guys. If you're having 4 A's and 4 B's and 4 C's, if you forgotten this, please go to the Turing machine construction example, that is 4.2, the construction of Turing machine. There I explain the same problem with the Turing machine. Let me just recall it within no time, right? See here we are having here what is the approach for it, what we have done. So if it is A, change it to X and search for the B. If it is B, change it to Y and search for the C. If it is C, change it to Z. In the reverse, we have to search for the X because we have to get the next A. When you got the X, and go right side and repeat the process whatever we have done. Like if it is A, change it to X and search for the B. If it is B, change it to Y, search for the C. If it is C, change it to Z and search for the X. Why you are searching for the X? After the X, we are going to find the next A to be considered. And if it is A, change it to X, search for the B. If it is B, change it to Y, search for the C. If it is C, change it to Z and search for the X. Like that you have to do it. And search for X. After making this last A as X, okay, last A as X, like this. And after that, if there is no A, we can conclude that there are no A, so that there must not be any B's and any C's. This is how it is going to be done. So this we have I've explained this with a right? State diagrams also, like we need to have a state called Q naught, right? So what it is going to do, Q naught. So the Q naught task is very simple here. If it is A, change it to X, search for the go in right direction, and hand over the task to Q1. And Q1 searching for the B. If it is B, change it to Y, and right direction give the task to Q2. Q2, if it is C, searching for C, Z, and go in left direction, and hand over the task to Q3. So Q3 is searching for the X. If it is X, don't do anything, go right side by giving the task to Q0, so that the same process is going to be repeated. And Q0 other than A, after making all the A's to X, if you find Y, don't do anything, just keep on right side and hand over the task to Q4. The Q4 is going to search for what? The delta. So delta stay option, then you can accept it or you can halt it. That's your wish. So then what are the other possibilities? While you are searching for it, B, after making any A to X, for example, second A to X and searching for the B, what are the possibilities you may encounter? Or third A to X and searching for the B, what are the possibilities? You may get A, Y, right? So if it is A, don't do anything, just keep on right side. If it is Y, don't do anything, just keep on right side, like that. And after making the second B as Y, searching for the second C, what you may get? B and first C is made to Z. Don't do anything, just keep on moving. So you may get B, don't do anything, just keep on moving right side. And if it is Z, don't do anything, just keep on moving right side. It's a Turing machine we are discussing here. Then Q3, after making the second C as Z, when you are searching for the second X, what you may get? Z, B, Y, A, X. So don't do anything for all. You may get immediately Z, don't do anything, just keep on moving left side. You may get B, don't do anything, just keep on moving left side. You may get Y, don't do anything, just keep on moving left side. If it is A, don't do anything, just keep on moving left side. Then if it is X, hand over the task to Q0. Other than A, you may get Y. Then Q4 should make sure that if there are no A's, and it should ensure that there are no C's and no B's. The Q4, while it is searching for the delta, it should encounter only Y's, keep on moving right side, Z, keep on moving right side. Other than that, if you get anything, means there is no possibility, so that we can say that the string is rejected. Other than these possibilities, the strings are going to be rejected. So this is the Turing machine, right? Then how we can convert this into the linear bounded automata, right? See, in the Turing machine, the tape is going to be like this, okay? And the end marker would be delta. But in LBA, we are going to have the tape with left hand marker and right hand marker, like less than and greater than. And here you are going to have A, B, 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 C, C, C. Right? Our process is going to be start from left hand marker. Right? So I'm saying that new state. So guys, it's very simple. Just write down whatever the transition diagram we have taken for the Turing machine as it is. Right? Let me copy it. So Q naught AXR, same, I'm just copying it. Q1, and what it is having, AR YYR, okay. Then BYZ. Q2, we are going to have BBR ZZR and CZL, same, all the symbols are same, right? Then you can write ZZL, BBL, YYL, same. I'm not doing anything with the remaining all the possibilities how we are doing for the Turing machine. And this is also same, like XXR and same YYR, okay. Then YYR ZZR, same thing. But here we are not going to have the delta. Here we are having left hand marker. Then you can stay there and you can accept it. But the process here started with the A, right? But you have to introduce a new state, QS, starting state, where you are going to have the left hand marker. Then you can do it. That's the only changes we have to make here. That's it. These are the only two changes. One is replace the delta with the greater than, and you have to introduce a new state for the left hand marker. then you may get it out. What is it, right? So, but Turing machine can utilize the space here and here, okay? But you can go, if it is delta delta, you can go left side, right side you can go, and you can change here if you want, for example. But here you can't go anywhere, only left side and stay. But for the right hand marker, right move is not allowed. For the left hand marker, left move is allowed. You can go to right and you can stay here, but you can here you can go left or stay here. That's a things, right? That's the only difference between the linear bounded automata and Turing machine. Means you can't change the space, you cannot use the extra space. So whenever you need extra space while you are doing the process, so such languages are not accepted by the LBA, then you can go for the Turing machines if you want more space, right? So that's what exactly the LBA. And guys, this is the end of ALC. So generally we have discussed all the languages, all the grammars, and all the machines. The hierarchy you have remembered, right? So regular languages, contextual languages, DCFL, right? So CFL and CSL, RCL, REL, and finally non-recursive enumerable language. Right? You know, right? What is a grammar to identify it? Regular languages means regular grammar. This is type 3. DCFL means unambiguous context-free grammar. It is nothing but type 2. CFL means any context-free grammar, same type 2 only. And CSL means context-sensitive grammar, type 1. Recursive language means, and both for these two, unrestricted grammar, that is type 0. And the machines are regular languages means finite state machine or finite automata. DCFL means deterministic push down automata. Okay, and CFL means push down automata. CSL means linear bounded automata, what we have discussed. Recursive language means Turing machine with halting. Recursive enumerable language means Turing machine. Non-recursive enumerable language means no Turing machine possible, no machine. That's it. The complete 5 units we have discussed about this. And these problems are undecidable problems and the closure properties. Nothing more than that, if you remember. First unit we have discussed about finite automata, minimization, conversions. Second unit we have discussed about especially PDA and context-free grammar. Third unit we have discussed about DCFL, DPDA. Right. And fourth unit we have discussed about Turing machine and conversions. Fifth unit, recursive languages, decidable properties, undecidable properties. That's it. So that is the end of it. Thank you guys.